Hello everybody. Today we're going to talk about one of the most in-depth things that we can do using slope and distance, which has sort of been the focus of the first 5 sections of this chapter. After this section, we're going to be switching gears to a different thing from Algebra 1, something else we want to review. But today we're going to talk about proving quadrilaterals with coordinates. So this is going to bring together all of the information we've talked about with the slope and the distance formulas. And then it's also going to bring back in quadrilaterals from chapter 11 in the first trimester. So we've seen bunches of different kinds of quadrilaterals. Remember, we made a flow chart of how all of those quadrilaterals mix with each other, how they're related to one another. We're going to use that information today. We're going to define some of these quadrilaterals again, just like we did back then. We're going to use some geometric definitions that maybe you haven't seen before for those quadrilaterals, but they all do work. And we're going to be able to prove that a figure is a quadrilateral if we only have 4 of the coordinates or 4 of the vertices. So first of all, we're going to talk about proving that something is a parallelogram. So in order for a figure to be a parallelogram, it has to be a quadrilateral with both pairs of opposite sides parallel. So I'll write that with both pairs of opposite sides parallel. That means that for us to prove that a figure is a parallelogram, somehow we have to prove, using the coordinates, that this shape has both pairs of opposite sides parallel. And there are actually 4 different ways we can do this. So when we have a list in this section, it's going to be 4 completely different strategies that you could use to prove that something is a parallelogram. The first thing we could use, the first method, is we could use slopes to prove that both the pairs of opposite sides have the same slope. So we'd use slopes, or the slope formula, to prove that both the pairs of opposite sides have the same slope. The other methods we use here are methods we could use because of other properties of parallelograms. So for this one, a parallelogram also has congruent opposite sides. We talked about that when we talked about parallelograms, congruent opposite sides. So another way we can prove that a figure is a parallelogram is we can prove that it has congruent opposite sides. So we could prove that the length of each pair of opposite sides is congruent using the distance formula. So distance formula. And if we use method 2, we don't need to prove that anything is parallel. We don't have to use the slopes at all. We can just use the side lengths to show that this is a parallelogram, because having congruent opposite sides is a property of parallelograms. Number 3, we could use both the slope and the distance formula to prove that one of the pairs of opposite sides is both congruent and parallel. Because if we prove that one pair of sides of a shape is congruent and parallel, that means that the other pair of sides also has to be, and this would be a parallelogram. So we're going to use slope and distance to prove that one pair of opposite sides is both congruent and parallel. And finally, the 4th method uses another property of parallelograms, and that is to prove that the diagonals of the parallelogram bisect each other, because any shape where the diagonals bisect each other is going to be a parallelogram. So we'll say diagonals bisect each other. And all of those are related to properties that we found in chapter 11 in the first try about parallelograms. We're just bringing them back here. So what you're going to have in this section is you're going to be given 4 vertices, 4 coordinates of a quadrilateral, and we're going to have to choose one of these methods to use to prove that this is a parallelogram. So in each of these examples today, you're given quadrilateral A, B, C, D. And one thing to remember about that, I'm just going to draw any quadrilateral here. I don't know. Oh, look, that one's a trapezoid. So we've got A, B, C, D. If we are writing the four letters like this, that means that when we go around the figure, A is connected to B is connected to C is connected to D, and D is connected to A. So if we want to prove something about the opposite sides in a parallelogram or in a quadrilateral like this, AB and CD or DC are opposites, and AD and BC are opposites. If we wanted to prove something about adjacent sides that are next to each other, we could prove something about AB and BC. So make sure that you're using the correct sides if you're using one of these methods that says, oh, we want to use the opposite sides or something like that. I'll explain what I mean here. So prove that the quadrilateral is a parallelogram. We're going to choose one of these four methods to use. We'll just use method 1 here. So method 1. You only need to use one of the methods. You don't need to use all four at all. So here in method 1, it says use slopes to prove that both pairs of opposite sides have the same slope. So I'm going to use the pairs of opposite sides of this figure. And again, it doesn't necessarily look like this, but this is a generic quadrilateral. So I need to prove that AD and BC have the same slope. And I need to prove that AB and CD have the same slope. So I'm going to write that here. I want to show that AB is parallel. Remember that parallel symbol we have. Show that AB is parallel to, what did we say, CD, and that BC is parallel to AD. So let's do that using slopes. So we use AB and CD over here. We're going to find the slope of AB. We're going to find the slope of CD. So the slope of AB is going to be y2 minus y1, so 4 minus 4 over x2 minus x1, 4 minus 0. Slope of CD is going to be y2 minus y1, 2 minus 2, over x2 minus x1, negative 1 minus 3. So slope here is going to be 0 over 4. Can't even see that, hold on. And the slope here is going to be 0 over negative 4. And in both of those instances, that would be a slope of 0. So these two sides have the same slope. That pair of opposite sides have the same slope. So we're halfway to proving that this is a parallelogram. We're going to do the same thing for the other pair of opposite sides. So we want to see that BC and AD also have the same slope. So we'll go in here and we'll say, all right, side BC has a slope of 2 minus 4 over 3 minus 4. And side AD has a slope of 2 minus 4 over negative 1 minus 0. And we'll do both of these. So we've got negative 2 over negative 1. And on this side, we have negative 2 over negative 1. And both of those are actually a slope of positive 2. So BC and AD have the same slope. So what we just showed is that both pairs of opposite sides are parallel. So I'm going to write that. I'm going to say, since both pairs of opposite sides have the same slope, I'm going to use a new geometry symbol here. We haven't seen this symbol yet, but it's hugely popular once you get past high school. It's a lazy geometry symbol. It's 3 dots in the shape of a triangle, and those 3 dots in the shape of a triangle mean the word therefore. So both pairs of opposite sides have the same slope. Therefore, ABCD is a parallelogram. And we have to put that at the end. We have to say, we did this math to show that my figure is a parallelogram. Because we're proving here, we're making a sort of a proof. And it says, prove that the quadrilateral is a parallelogram. So here's my reasoning. You can look over here at my math and make sure I'm correct. And therefore, this figure is a parallelogram. This is going to be a long video. I can kind of tell that. I'm sorry about that. The next one here, we're going to prove that a shape is a rectangle. So first of all, we're going to define a rectangle. And for our purposes, a rectangle is a parallelogram with at least one right angle. At least one right angle. Now, you might be going, hey, wait a minute. rectangles have 4 right angles. Why is this the definition that we're going to use for a rectangle? So remember that this is a definition that is the minimal definition. This is the least that we could say and still have this definition be talking about a rectangle. So notice here it says we start with a parallelogram. It doesn't say starting from quadrilateral. We already have to know that a shape is a parallelogram because all rectangles are parallelograms. So if we have a parallelogram and one of the angles in that parallelogram is a right angle, so let's show that here. I'll just draw a parallelogram. There's a parallelogram. And say this angle is a right angle. And in parallelogram, one thing that we knew is that this opposite angle is a parallelogram as well. Hold on just a minute, that music will stop in a second. So our 2 right angles are opposite from each other and the same, which also follows that this angle and this angle must be right angles because of supplementary angles. So if we have one angle that's right, the rest of the angles in our parallelogram will also be right angles, leading this to be a rectangle. So there are 3 methods for proving that a figure is a rectangle. Method number 1 is first, prove the figure is a parallelogram with any method used above. So we need to use the parallelogram methods while we're proving rectangles because part of the definition of rectangle is that that shape is also a parallelogram. So after we show that the parallelogram, or a figure is a parallelogram, then we're going to use slopes to prove that a right angle is present. If we use the slope of 2 sides that are adjacent to one another, so like this side and this side, and we see that those slopes are opposite reciprocals, we know that these 2 sides are perpendicular to each other, so we've created a right angle. So that's one way that we can show that this is a rectangle. Another way is we can prove the figure is a parallelogram, again, using any of the methods from up above. Then we could use the distance formula. So distance formula to show that the diagonals are congruent. And that goes back to something we learned in chapter 11. We talked about how the diagonals of a rectangle are always congruent. Another thing we could do is we could not prove that the figure is a parallelogram. So without proving that the figure is a parallelogram, we could prove that all 4 angles are right angles using the slope. So if we found the slope between every pair of points or every point, then we could say if all 4 of those were right angles, then we would know that this was a rectangle as well, because another way we could define a rectangle is a quadrilateral with 4 right angles, and we could skip over the parallelogram part entirely. Once again, you can pick any of the methods you want to use here. You don't have to use all 3 for sure. So we are given a quadrilateral, and we want to prove that that quadrilateral is a rectangle. So we're just going to use method 1 again here. But again, you can experiment. You can choose any method you want. You can switch things around in your worksheet, decide to try different ways of proving, see if there's one that you like best. So in method 1, we have to prove that the figure is a parallelogram with the method used above. So we'll do the same thing we did up above, and we'll show that the 2 opposite sides are parallel and the other 2 opposite sides are parallel. And again, we have quadrilateral A, B, C, D. So the pairs of parallel sides are A, B, and C, D. That's one pair of parallel sides. The other pair of opposite sides are B, C, and A, D. So down here, we're going to prove that these 2 sides are parallel and these 2 sides are parallel using the slope formula. So AB, I'm going to use the points from up here. We're going to do y2 minus y1, negative 3 minus 3 over x2 minus x1, 4 minus 0. We've got CD, so we've got 1 minus negative 5 over negative 3 minus 1. And then AB is then negative 6 over 4. CD is then 1 minus negative 5 is 6 over negative 4. Both of those are the same number. They're both negative 3 halves if you simplify them down. Then we are going to do the same thing for BC and AD. So in BC, we've got negative 5 minus negative 3 over 1 minus 4. And for AD, we've got 1 minus 3 over negative 3 minus 0. And so negative 5 minus negative 3 is negative 2. 1 minus 4 is negative 3. And then over here, 1 minus 3 is negative 2. Negative 3 minus 0 is negative 3. And so both of those simplify to 2/3. So we just did method 1 from up above. We've shown that this now is a parallelogram because it's got an opposite side, or a pair of opposite sides with the same slope, and another pair of opposite sides with the same slope. This can also show that our quadrilateral is a rectangle because the next part, using slopes to prove that a right angle is present, is really easy here. Here is one pair of sides with a slope of negative 3/2. Here is the other pair of sides with a slope of 2/3, and you might notice that those are opposite reciprocals. Opposite reciprocals. Which means that those sides are perpendicular to one another, meaning that there are right angles at the corners, at the vertices of this quadrilateral. So we're going to go over here, we're going to write a summary of what we've done as the proof. So we're going to say both pairs of opposite sides are parallel. So both pairs of opposite sides are parallel. And the slopes of the pairs are opposite reciprocals. So, and the slopes of the pairs are opposite reciprocals. We'll use our fancy geometry symbol here. We'll say therefore, dot, 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 therefore, ABCD is a rectangle. And so we can check the math for this over on this side. We can see that we're right. Therefore, we've proven that this shape is a rectangle. All right, we are halfway done. Let's get through this. On the next side, we have 3 more shapes that we can use. We're only going to do 2 more example proofs though. So the next one we're going to talk about is a rhombus. We want to prove that a figure, a quadrilateral, is a rhombus. And the definition that we're going to go off of today is that a rhombus is a parallelogram with at least two consecutive congruent sides. Okay? And again, that's not the definition of a parallel or of a rhombus that we used before, but it does work. Notice we start with a parallelogram here, not a quadrilateral, so we're first showing that something's a parallelogram. And it's got to have 2 consecutive congruent sides. So if we draw a parallelogram up here, and if in this parallelogram, we already know that the sides are parallel to one another, we say that this side and this side are congruent, then we know, because it's a parallelogram, that this top side and the opposite side are also congruent, and this side and this side are also congruent. So if at least 2 consecutive, next to each other, congruent sides are there, then all 4 of the sides are congruent, which gives us a rhombus. So just 2 methods for proving here. So to prove a quadrilateral is a rhombus, we could, number 1, first prove that the figure is a parallelogram. We'll start there. Then we could use the distance formula. The distance formula to show that at least 2 consecutive sides are congruent. All right, and that would work as a proof. Another way that we could prove this is we could, without proving a parallelogram, prove that the diagonals are perpendicular bisectors. And this comes off of what we were talking about, again, way back in chapter 11. We talked about that rhombuses were a type of kite. And so we could use the idea of the diagonals of a kite being perpendicular to each other and bisecting each other to show that this is a rhombus. All right, and I'm going to write over here, it doesn't really say how to do this. We're going to use the slope formula and the midpoint formula to show that 2 lines are perpendicular bisectors. So in this case, let's try method 2, since it's a little bit different and I don't want to go through the same process again. We've got quadrilateral ABCD, and we're not going to start by proving that it's a parallelogram. We're going to just start by showing that the diagonals are perpendicular bisectors. And if you need to, in your head, think about what are the diagonals from these four, remember that you have 4 points, and A, B, C, D are all in a row around each other. So this could be A, B, C, D, like that. So if we're talking about diagonals, one of the diagonals is AC and one is BD. So that's what we're going to use. So first here, we're going to prove that they are perpendicular. So we're going to use the slope formula, and we want to prove that AC is perpendicular to BD. So we're going to use the slope formula for those two. So for AC, we've got y2 minus y1, negative 1 minus 5, over x2 minus x1, so 2 minus negative 4. For BD, we've got 0 minus 4 over negative 3 minus 1. So negative 1 minus 5 is negative 6 over 2 minus negative 4 is positive 6. 0 minus 4 is negative 4. Negative 3 minus 1 is negative 4. And both of these, well, first this one simplifies to negative 1, and then BD simplifies to positive 1. And if you remember, negative 1 and positive 1 are opposite reciprocals. So these two are perpendicular. We can say AC is perpendicular to BD, since both of these slopes are opposite reciprocals. So we've got the perpendicular part. Now we need to make it the bisector part. To show that AC and BD bisect each other, we're going to do something kind of clever. We're going to show that the midpoint of AC is the same as the midpoint of BD. So right halfway at AC is the same as right halfway across BD. And if that's true, then these are bisecting one another. So we're going to use the midpoint formula. So we're going to find the midpoint of AC, and we're going to find the midpoint of BD, and we're going to see if they're the same. So for AC, remember we're finding the average, so x1 plus x2 over 2, so that's going to be negative 4 plus 2 over 2, and then y1 plus y2, 5 plus negative 1 over 2. And if we simplify that down, negative 4 plus 2 is negative 2, divided by 2 is negative 1, and then 5 plus negative 1 is 4, divided by 2 is 2. So the midpoint of AC is negative 1, 2. For BD, we've got a midpoint of 1 plus negative 3 over 2. And we have the y coordinate for that of 4 plus 0 over 2. So we simplify this. 1 plus negative 3 is negative 2 over 2. That's going to be negative 1. And then 4 over 2 is 2. They have the same midpoint, which means the diagonals bisect each other. So we found, up here, we found perpendicular diagonals. Perpendicular diagonals. Down here we found bisecting diagonals. Bisecting diagonals. And since we found both of those pieces of information, then we can say, therefore, A, B, C, D is a rhombus. Rhombus. And we can check over here, and somebody who was looking to make sure we were right could check on our math and say, yeah, they're right with that. The next one here is a square. We're not going to do an example of a square because these notes would be way too long, and these are pretty similar to the other arguments that we've seen or the other methods that we've seen. So a square is a parallelogram that's both a rectangle and a rhombus. Both a rectangle and a rhombus. If you remember back to when we made a flow chart with all of our shapes, we had two branches coming down to a square. One was rectangles and one was rhombuses, and a square was both. So we're going to use the fact that it's a rectangle and the fact that it's a rhombus to prove that something is a square. So we're starting with a quadrilateral, and to prove that quadrilateral is a square, first prove that it's a parallelogram. So we're going to start by proving that it's parallelogram, just like it says up here. Then we're going to use slope to show at least one right angle. That way we'll be fulfilling the rectangle portion. And we'll use the distance formula to show that at least two consecutive sides are congruent. That's fulfilling the rhombus. So really we're doing almost three separate proofs for a square. We're proving that it is a parallelogram. So we're using that first set of stuff. Then we're going to prove that it's a rectangle using the second set of methods we came up with. Then we're going to prove that it's a rhombus using this third set of methods. And you could use different methods from each section, but you would be able to use one method from each section and prove that that figure is a square. All right, and then finally we're going to talk about proving an isosceles trapezoid. So an isosceles trapezoid, like you may remember, is a shape that looks like this. We're not proving any old trapezoid. We're not just proving a general trapezoid. We're proving an isosceles trapezoid, which means that the two non-base sides, the two non-parallel sides, are congruent. All right, we'll write that down here in our definition. In an isosceles trapezoid, it is a quadrilateral with exactly one pair of parallel sides. So that would be this top and this bottom side, with non-parallel sides congruent. Non-parallel sides congruent. So we're going to say to prove that a quadrilateral is, and then we should say not parallelogram here. We should say isosceles trapezoid. Isosceles trapezoid. We can use either of these methods. So first, we can prove that the figure is a trapezoid, which is just one pair of parallel sides. And we can do that using slope to show that a pair of sides are parallel. And we can prove that the other two sides, the ones that are not parallel, are congruent using the distance formula. The other thing we could do is first prove that the figure is a trapezoid, so one pair of parallel sides is congruent, or is parallel using slope. Then we could prove that the diagonals are congruent, because if any trapezoid has congruent diagonals, then that trapezoid is isosceles. So we're going to go in here and we're going to say, all right, we'll use method one. So we have quadrilateral ABCD again. And what I'm going to do, because I don't know what sides are parallel here. I don't know which of the sides are the ones that are going to be parallel. I don't know if it's AC and BD or BC and AD. So I'm going to find the slope between every pair of points. I'm going to find the slope of each side here. So I'm going to come down here and I'm going to say, okay, well, it could be side AB, or it could be side BC, side CD, or side AD. So I'm going to check all of those and see which of these sides are the parallel sides. So for AB, we're going to use the slope formula, -4 minus -2 over 0 minus -2. So -4 minus -2 is -2. -2 divided by 2 is -1. So AB has a slope of -1. BC will come through here. So we've got -5 minus -4 over -2 minus 0. So -5 minus -4 is -1. -1 over -2 is positive 1/2. So BC has a slope of 1/2. Then we'll do CD. So CD is -4 minus -5 over -3 minus -2. So -4 minus -5 is positive 1 over -3 minus -2, which is -1. Positive 1 over -1 is going to be -1. So CD has a slope of -1. And then AD, we've got -4 minus -2 over -3 minus -2. So -4 minus -2 is -2. -3 minus -2 is -1. So -2 over -1 is positive 2. So we've got all four slopes, and we can easily see which sides are parallel by looking at the slopes, because AB and CD have the same slope, which means that AB and CD are the pair of parallel sides. I'm going to write that. AB is parallel to CD. So we've got the first part of our proof done. And then we also need to prove that the other two sides are congruent using the distance formula. So the other two sides that are not AB and CD are BC and AD. So we'll write those over here, BC and AD. And for BC and AD, we're going to use the distance formula to show that they're the same length, because that fulfills the other requirements of an isosceles trapezoid. So BC here, we'll make the distance formula, and we're going to go with x2 minus x1 squared. So we're going to say that that is negative 2 minus 0 squared plus y2 minus y1 squared. So that's going to be negative 5 minus negative 4 squared. And if we simplify this all out, we get the square root of negative 2 minus 0 is negative 2 squared plus negative 5 minus negative 4 is going to be negative 1 squared. And that gives us 4 plus 1. So this is the square root of 5. And then we'll check AD. So that's going to be the distance formula. We've got x2 minus x1 squared, so negative 3 minus negative 2 squared, plus y2 minus y1 squared, so negative 4 minus negative 2 squared. Simplify this out. So we've got negative 1 squared plus negative 2 squared. That's going to give us 1 plus 4, which means AD is also the square root of 5. So we found that the non-parallel sides are congruent. So we'll use the congruency symbol there. So we found that AB is parallel to CD, the opposite sides are parallel, and the other two, the non-parallel sides, are congruent. Therefore, ABCD is a trapezoid. And actually, I'm going to write isosceles here. It's an isosceles trapezoid. Whew, that was a long one today, but we are done. Go ahead and work on your worksheet for this section, and the answer key will be posted tomorrow. Thank you.